Today we're graphing rational functions. A rational function, of course, is a function with a variable in the denominator. This is our most basic rational function, 1 over x. Part of our work today will be including what makes a fraction undefined, where are the vertical and horizontal asymptotes of rational functions, and how can I graph them using transformations. First and most importantly, we need to remember that a fraction is undefined when the denominator is equal to 0. So for example, in this first function here, if we were to substitute x is equal to 0, what we were trying to do is take the number 3 and divide it by 0. And of course, we all know that that is undefined. We can't take the number 3 and split it into 0 groups. For this next function here, when is this fraction going to be undefined? Well, all that matters when we're asked that question is what's in the denominator, because the denominator cannot be 0. So what value would make it 0? We simply take the denominator value and set it equal to 0, and then solve that equation. And we get here that if we were to plug in the value of -2, this fraction would be undefined, because on the bottom, we would get -2 plus 2, and we'd be trying to calculate -2 over 0, which of course we cannot do. Now in this last one, we look again at the same question. When is this fraction going to be undefined? And all that matters is what the denominator. When would the denominator equal 0? So we take the denominator, 2x minus 4, and set it equal to 0. Solve a little equation here, and we get 2x is equal to 4. So here x is equal to 2. So if we substituted x equals 2, the denominator would have a value of 0, and we cannot divide by 0. Now, why do we care when a fraction is undefined? Well, a very common question when we're dealing with rational functions is we're going to have to determine the location of the vertical asymptotes of an equation. And what we're going to realize is that the x value where a fraction is undefined is that vertical asymptote. So just to refresh on the vertical asymptote, here's the graph of our basic function, y is equal to 1 over x. And as we can see, the general shape here, we'll notice that our general shape in the graph, no matter where we are, is never going to touch the x-axis and never going to touch the y-axis. And when we have a point on the graph, or a line on the graph, that our graph gets very close to, but never actually touches, that's where we have our asymptotes. What we can see here is that our first asymptote is going to be at the line x is equal to 0, which is, of course, the y-axis. Now, as we can see from the equation, if we were to sub in x is equal to 0, that would make the denominator 0, which would make the fraction undefined. So we have our vertical asymptote at x equals 0. Now going back to this problem where we're asked to determine the vertical asymptote of each equation. So now we know that the vertical asymptote is just what makes the denominator equal to 0. So here we're going to take this denominator and set it equal to 0. And then we'll solve the mini equation here. So we get x is equal to 2. Now, that communicates two things with us. That communicates that if we actually substituted the x value of 2, we would have a undefined fraction because the denominator would be 0. But x is equal to 2 is also the equation of a vertical line. And on a graph, that will be our vertical asymptote. Now this next example over here, where would the vertical asymptote be? Well, we take that denominator and ask ourselves when would that be equal to 0? Because at that x value is when our fraction is undefined. So on a graph, that would be our vertical asymptote. Now we know how to find the vertical asymptote of a rational function. There also is a horizontal asymptote. Going back to look at the graph that we were looking at before, we also see that our function here will actually never touch the x-axis. or in other words, the equation where y is equal to 0. So our function, y is equal to 1 over x, will never have an output of 0. No matter what x value we choose, we will never be able to get it to equal to 0. A little background knowledge as to why do we see a horizontal asymptote at y equals 0. So we look at our parent function here, y is equal to 1 over x. And let's actually think about it in a slightly contextual situation. So let's pretend that instead of 1 over x, we're imagining that one pizza is being split amongst a group of friends. Now, when we start with one person, so if x was equal to 1, that person's getting a whole pizza. Now, if there are two people sharing a pizza, each person obviously gets half a pizza. If 3 people were sharing a pizza, there'd be 1/3 of a pizza every person would get. The idea is we have a pizza, and all we're doing is we're splitting it into smaller and smaller pieces as we increase the number of friends that are going to be sharing the pizza with us. But no matter how small I make the pieces for our friends to get, albeit they could be so small, it doesn't even pay to even try to call it a piece of pizza. No matter how small they're cut up, we still have a piece of pizza. We have not lost the original pizza. We have just cut it into super small pieces. So if x is measuring the number of friends that are sharing a pizza, and y is the amount of pizza that each person gets, it's never going to be 0 because someone's going to get some piece of pizza. No matter how small it will be, we will never have no pizza to give. Now, another important example when thinking about horizontal asymptotes would be an equation like y is equal to 1 over x plus 3, which is going to be important to be read also as 3 plus 1 over x, just switching the order of the addition. Now, why? So what we're thinking about here is looking at this format. When we choose the value of x, the way that y will be calculated is we're going to take the number 3 and we're going to add some fraction to it based on whatever that x is going to be. So we obviously can't use x equals 0 because that would make our denominator undefined, and that would be where our vertical asymptote is. So let's start with x is equal to 1. So if x is equal to 1, we're taking 3, and then we're going to add 1 over 1. So we're going to take 3 and add 1, and that will leave us with 4. Now if x is 2, we are going to start at 3, and we're going to add 1 over 2. So in other words, that's going to leave us with 3.5. When we sub in x equals 3, we start at 3, and then we add 1 over 3, so we get 3 1/3. When we start at 4, we have 3, and we add 1 over 4, so now we have 3 1/4. Oh, and last time if we put x as 5, we're going to have 3, and then we're going to add 1 over 5. And then, of course, that leaves us with 3 1/4. Excuse me, 1/5. Now, what are we noticing? We're noticing that these y values are decreasing. But what are they decreasing towards? Well, the pattern that we see is 4, 3.5, 3 1/3, 3 1/4, 3 1/5, 3 1/6, 3 1/7. They're getting closer and closer and closer to 3 because we're always starting with the number 3, but we're adding a number that gets smaller and smaller every single time. So we're going to start with 3, and we're always going to add something. And if we're always adding something, we are always going to be a little bit more than 3, no matter what we do. So we know that our y value would never touch 3 because the fraction we're adding, albeit as small as 1/1000th, that's still a little bit bigger than 3 if we add it to the number 3. So we can see that our horizontal asymptote here would actually be at y is equal to 3. Now as we can see, this number here, our y value, is getting bigger and bigger and bigger. It always has 2 as the number of wholes, but the fraction that's being added to it is getting a little bit bigger every single time. Now, yes, this number is going to keep getting bigger and bigger and bigger, but it's never ever going to be 3 because we're starting with 3 and we are always subtracting something. Now, if we compare the number 3 to 3 and always subtracting something, that number 3 is always going to be bigger no matter what we subtract. Even if our x value is negative 1,000, we'd start at 3 and subtract 1/1000th, which would lead us to 2 and 999 1,000ths. However, that number is still less than 3.